graph below is that of f of x, which gives the rate of change of the amount of water in a reservoir measured in thousands of gallons of water a day as a function of x, the number of days that have passed. Part A, when is there the most water in the reservoir? Okay, so let's analyze this graph. In this beginning interval from here until the first time intercept, we see that the graph given is below the x-axis, and that means that the amount of water in the reservoir is decreasing for this entire time. And so I don't know how much water was in the reservoir at the beginning of this experiment at time 0, but I know that it was the amount was decreasing all the way until we get to around 60 or whatever that intercept is there. And then going from this intercept to the next intercept, this whole region in here, because this function given is positive, that means that the amount of water in the reservoir is increasing for the entire time. And it sure feels like the amount that we lose here is more than made up for by the amount that we gain over here. In fact, it's really comparing the areas, right? Like whatever the area of this thing is, that's a measure of the exact amount of water lost in the reservoir during this time period. But then the area of this is so much bigger that it more than makes up for the water lost there. So it feels like the maximum at the moment is right around 250. And then if we look at the end part from here until the end of this graph, again, the given graph is below the x-axis, the horizontal axis, and so the amount of water in the reservoir is decreasing for this entire time period here. So the amount of water is decreasing, then increasing a bunch more than it decreased, and then decreasing again. So just thinking about that, it seems like our answer here is 250. Okay, part B, can you tell how much water is there at that time? The answer is no. I know for sure that the area of the orange is how much water is lost in the first 60-ish days, and then the area in the purple is how much you gain from time 60 until time 250, and then we lose whatever this area is here, but without knowing how much water we had at the start, all we can say is how much we've gained or lost, but not actually how much is in there at any moment in time. Part C, by about approximately how much does the water level change over the first 50 days? Show how you got your answer. Okay, so the first 50 days is part of this orange, but it's not all the way to the end of the orange because 50 looks like it's right around there. So let's go with a different color. How about blue? So I'm going to put my vertical line right there at 50. So this, and then I'm going to put another vertical line here. And then I'm going to put a horizontal there. And even though this is curvy, I'm going to approximate it with a straight line there. And if I approximate that curvy part of the orange region with straight lines, we just get a trapezoid. And so the goal is to just find the area of that trapezoid. Whatever that is, that's how much water we lost over the course of the first 50 days. So to find the area of the trapezoid, some folks like to make the trapezoid part rectangle, that's the part above, and then part triangle, a right triangle, which is below. I'm going to be fancy because I know the area of a trapezoid formula, but if you don't know it, you're welcome to cut it into a rectangle and a triangle. So the area of a trapezoid is half the height times the sum of the bases, where the bases are the parallel sides. Okay, so let's see the height. So this trapezoid maybe is on its side. So the parallel sides are here and here. And so that means the height is actually this horizontal thing. And the length of that height is 50 days. So it's half of 50 times, and then the sum of the bases. So now we're just looking for the lengths of those parallel lines there. Okay, so the first parallel line, I've actually kind of drawn it poorly. It doesn't come all the way down there, so we're going to stop it right there and then try to estimate that number, maybe negative 0.8. It's kind of hard for me to see the hash marks given the lines I've drawn on top of them, but I'll call that negative 0.8. Or I'll just call it 0.8. treating it like a length, so it's positive, plus, and then the other one, this one we really have to do a job here of estimating. So it looks like 50 hits the curve right around there, and then we're coming straight over here and guessing that number. I'll call it 0.2. And so 0.2 is our estimate for the length of this base right here, that vertical line. And so we crunch the numbers here, and in this case we just get 25. And so 25 is the amount of water, the amount of change in the water over the course of those 50 days. And so it's measured in thousands of gallons. But in this case, because we see that the graph is below the x-axis, we know that this is actually a decrease, a loss. So 25,000 gallons, I'll say lost. There are different ways to say that. You could also say negative 25,000 gallons if you wish. So that's the amount of change, 25,000 gallons lost. D, how does the amount of water at day 300 compare to the amount of water at day 0? Okay, let's take a look. So 300 is not quite the end of this graph, so I'll put a line here at 300. 300 right there. And so I'm interested in knowing, we've got the amount of water decreasing by this area here for all of the orange, including the extra stuff from 50 to 60. But then we've got purple area gain, and then we've got part of this red area lost up until that line, but don't go all the way out here. So the question is just which one wins? Is there more loss or is there more gain? So really we're comparing the area of the purple to the area of all the orange plus the red, but only up until this thing right here. So that part of the red. And it sure feels like purple wins, even though orange and red, there's two different negative pieces here, but it seems like the positive outweighs the negative. So how does the amount of water compare? At day 300, there is more water than at day 0 because the amount of water gained is more than the amount lost. I just took a quick peek at the answer key at the back of this document, and it references the area above the x-axis being greater than the area below. That's, I think, a stronger answer than mine, because mine doesn't technically reference the graph. I described things in terms of the graph. I said the area above is more than the area below, but I didn't actually write that part. So in retrospect, I think it's probably better to write the answer that's in the key, because it makes specific reference to the given graph in this one. In fact, maybe I'll add that here. Area above is greater than area below. E, draw a possible sketch of the integral from a to x of f of x dx. Your sketch should be accurate enough to reveal maximums and minimums and inflection points in their correct locations. However, don't worry too much about getting the exact y values of your graph. Okay, so let's draw a graph here. All right, so we're gonna get some axes here. And we're gonna start at day 0 and go out until whatever the end of the graph was, 300 something, 360. Something like that. And the problem here has this sort of nebulous a inside of the integral. That means you can pick any a that you want. And so, for example, you could let a equal 0. And we know that this integral represents the area accumulation function as we start at 0 and then increase x proceeding to the right. We're just sweeping out area, sweeping out negative area here, sweeping out positive area here, and then sweeping out some more negative area. And we're just going to accumulate that area as we go, as we sweep to the right. That said, I'm going to make my graph look like the one in the answer key. And the one in the answer key starts somewhat arbitrarily up at around 50. Doesn't even matter what the number is, but they just started right there. In fact, you can start your graph any point you want to. It doesn't even need to be on the y-axis. You can pick any point between 0 and 350 at any y value, any height, but I'll match the answer key. So they started up there, and then they say, okay, as we sweep to the right between 0 and 60, we are losing area fast in the beginning because it's really low down here, and then we're losing area still, but less and less, right? This is negative, but not as negative as it was over here. So that means we're going to be decreasing quickly in the beginning, slower and slower until we get to 60. So I'm going to put a dot at 60 right here. I'll call that 60. And we're decreasing fast in the beginning, slower as we get there. And in fact, we should actually bottom out at 60 because we're about to turn around. We're about to start gaining area. And looking at the picture up above, we gain area from 60 until 250, with the maximum gain happening at 150. So 60 until 250, not to scale, but that's okay, with the maximum area gained right around 150. So that means that we are increasing slowly in the beginning, faster, 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 until we get to 150. And at 150, the graph at the top of this page is as tall as possible, which means you are gaining area as quickly as you ever will. You are increasing as quickly as you ever will. And then as you pass 150 and go to 250, you are still increasing, still grabbing positive area, but not as quickly. And so we're not going to go, we're going to start to get flatter and flatter, still going up, but not increasing as quickly. And so 150 is your inflection point right there. Over here, we'll call this one the local min. And then I think this guy up here is going to be a max, but let's make sure we're good there. So from 250 until the end of the graph, we are negative, which means that the function I'm graphing is going to be decreasing the whole way with a minimum decrease right here around like 350, 340, something like that. And then still decreasing after that, but not quite as quickly. So 340, I think, is a point that I'm going to mark down. All right, so let's finish this one up. So I've got 340 here. And so we are going to decrease slowly at first, faster and faster and faster, until we get to 340, at which point we still decrease, but not quite as quickly. And so 340 is another point of inflection. It's the biggest decrease in the given graph. And let's go ahead and put our maximum right there at 250. And again, because you could start at any point you wanted to, your graph isn't going to necessarily look exactly like mine. I started specifically at that point, but any vertical shift of this graph is fine. But make sure you've got the same x values for the min, the max, and the 2 points of inflection.